So far we have discussed sequence, their convergences and their applications in statistics. We have seen how convergence of series and convergence of sequence can be used to get large sample results in statistics. We have discussed series given their definition and discussed convergence using first principle, and then we have used some tests to get convergence results. So, in our last module we have discussed some tests and their applications. However, in this module we shall start with a few more examples using the tests of the previous module. We also discuss big O and small o notations and their applications in finding the convergence of different series. In particular, we discuss Gauss's test for series, and then we pass on to our next topic, which is sequence of functions, and also discuss some concepts for pointwise convergence and some other properties. So, we have seen sequences and series and their convergences in our previous modules, and in this module we shall start with some further examples of series convergence and then proceed to our next topics, for example big O and small o notations and their use in Gauss's test, sequence of functions, their convergences, in particular pointwise convergences, and some examples. So, let us start with some few more examples on series convergence. So, consider the series summation n from 1 to infinity n plus 1 whole to the power minus n. Naturally, the nth term in this case is n plus 1 whole to the power minus n, and we find that a n whole to the power 1 by n is nothing but 1 by n plus 1. Therefore, the limit of a n to the power 1 by n is 0, which is less than 1, and hence by Cauchy's root test the series converges. Consider our next example, where the series has the nth term n to the power n by n factorial. Naturally, there is a power in n, that is we are using n to the power n. Therefore, while we take the ratio of a n plus 1 and a n, we get 1 plus 1 by n whole to the power n. Now, it is already known that limit of 1 plus 1 by n whole to the power n is nothing but our e, and which is greater than 1. Therefore, from the ratio test the series converges. Consider our next example, which has some peculiar behavior, where the even terms are powers of 3 and odd terms are the negative powers of 3. That is, if we consider the nth to n an even term and odd term, we get a to n as 3 to the power n and a to n plus 1 as 3 to the power minus n, where n is starting from 0 to up to infinity. Then limit of a to n to the power 1 by 2n to the power 1 by 2n is root over 3, and limit of a to n plus 1 to the power 1 by 2n plus 1 is 1 by square root of 3. Therefore, the limit superior of a n is square root of 3, which exceeds 1, and hence by root test the series converges. Next, consider our next example. We have a series whose nth term is given by 2 plus log n to the power minus 1, and we note that this nth term is a decreasing quantity. Now, we shall use Cauchy's condensation test. So, for some b, positive b, integer b, we consider b to the power n, a in suffix b to the power n, which comes out as b to the power n divided by 2 plus n log b. Since by definition b is greater than 1, b to the power n is also greater than 1, and hence we get b to the power n a n, b to the power a b to the power n as b to the power n divided by 2 plus n log b, which exceeds 1 by 2 plus n log b. Now, b is a constant and summation 1 by 2 plus n log b is known to be divergent. Hence, the original series diverges by Cauchy condensation test. Next, consider our new example. It is again a series with nth term n log n whole to the power minus p. Now again we shall use Cauchy condensation test. So we consider some b greater than 1 and take the term b to the power n multiplied by a b to the power n, which comes out as b to the power n minus np whole thing divided by n log b whole to the power p. Now for p greater than 1, b to the power n minus np is less than 1. Since b is a constant, we get by comparison test that the series summation sum over n to the power minus p converges for p greater than 1. However, for p equal to 1, b to the power n, a b to the power n equal to comes out as 1 by n log b, which is divergent. Then for p less than 1, we get b to the power n minus np is greater than 1, and hence b to the power n, a b to the power n exceeds 1 by n log b whole to the power p. Since b is a constant, we get by comparison test that the series diverges for p less than 1. In our next example, we revisited the p series, the convergence of p series. So as already discussed, the nth term for a p series is n to the power minus p, and we also observe that this nth term is decreasing in n. Now b to the power n for some b greater than 1, b to the power n, a b to the power n is nothing but b to the power n minus np. Now for p greater than 1, b to the power 1 minus p is less than 1, and hence summation b to the power n, a b to the power n becomes a geometric series with common ratio less than unity. Thus the series converges for p greater than 1. However, for p equal to 1, b to the power n, a b to the power n comes out as 1, which is a constant, and therefore by definition the corresponding series diverges. Next, for p less than 1, we have b to the power 1 minus p exceeding 1, and hence from the properties of geometric series the series also diverges. So now we shall introduce some important notations which are very useful in large sample scenario. We start with BGO notations. The symbol BGO was first introduced by E. Landau. The letter O is used to indicate growth rate of a function. Growth rate is commonly known as its order. So from the acronym, from the first letter of order, we get the notation BGO was introduced. These notations are often useful to compare growth rate and decrease rate of functions. Suppose an and bn are two sequences. Then an equal to BGO of bn as n tends to infinity if and only if the ratio an by bn is uniformly bounded for n greater than or equal to n naught. That is, there exists a constant m and n naught such that modulus an by bn is less than capital M whenever n exceeds n naught. However, an equal to BGO of 1 implies that an is itself bounded for large n. Now, if an equal to BGO of bn, then it implies an by bn the ratio is BGO of 1, and then an and bn are said to grow or shrink in the same rate. Illustrate the concepts of BGO by means of some examples. In our first example, consider the polynomial, the 3 degree, third degree polynomial a naught plus a1n plus a2n square plus a3n cube. Then we can write the polynomial as BGO of n cube, whatever be the coefficients. However, the polynomial with inverse powers of n, that is a1 by n plus a2 by n square plus a3 by n cube, is represented by BGO of n to the power minus 1. If an is a finite sum or difference of a number of functions, then the fastest growing quantity gives the order. For example, consider an equal to n square plus n plus log n. Then naturally the fastest growing quantity is n square. Thus we write n as or BGO of n square as n tends to infinity. On the other hand, if an is a product of several factors, the constant term is omitted from the order relation. As another example, consider the polynomial an equal to 4 plus 6n cube minus twice n5, n to the power 5. Actually, by means of this example, we shall show the choice of n naught and capital N. Naturally, here the highest power is 5, and hence conventionally n is big O of n to the power 5. However, if we follow the definition, we need the auxiliary sequence Bn. Now, absolute value of n is less than or equal to 4 plus 6n cube plus 2n to the power 5, which is again less than or equal to 4 plus 6n to the power 5 plus 2n to the power 5 equals 12n to the power 5 whenever n exceeds 1. Thus, we get m as 12, n naught as unity, and Bn as n to the power 5. Let us consider our next example. Actually, big O notation is useful in computer science to compare efficiency. Suppose we have a program of size n where the size is defined in some sense, in some related sense of computer programming, and the program of size n takes the time n, which equals n square plus 2n to give the output. Another size n program for the same purpose takes the time Bn equal to n cube minus n square to give the output. Naturally, the program taking less time is efficient. Now, the latter program has a leading term n cube, which grows at a faster rate than Thus, big O notation can be used to indicate the time efficiency. Since n equal to big O of n square, it is more efficient. So, next we shall define another notation which is known as small o notation. The small o notation is used to capture the growth comparison of two quantities. If an and bn are two sequences, then an equal to small o of bn as n tends to infinity if for every positive constant epsilon there exists some n naught depending on epsilon such that absolute value of an by bn is less than epsilon whenever n exceeds n naught. This simply means that n equal to small o of bn if and only if the limit of n by bn equals 0. Naturally, small o is different from big O in the sense that for the former the inequality has to be true for some m, whereas for the latter the inequality is to be satisfied for every positive epsilon. Thus, n equal to small o of bn implies an is also big O of bn, but the converse is not true. Now, after introducing big O and small o notations, it is natural to consider an example in the field of series and sequence. So, we shall discuss Gauss's test using big O notation. Suppose we have a series with a nth term an such that, and an is positive, such that an by an plus 1 equals 1 plus alpha by n plus beta n divided by n to the power p, where p is greater than 1 and beta n is a bounded sequence. Then the series converges if alpha greater than 1 and diverges if alpha less than or equal to 1. So, looking at the last term, that is beta n by n to the power p, we can write the ratio an by an plus 1 in terms of big O. Actually, an by an plus 1 can be expressed as 1 plus alpha by n plus big O of n to the power minus p with p greater than 1. Then, as earlier, the series converges if alpha greater than 1 and diverges if alpha less than or equal to 1. Naturally, the criteria can be written more conveniently using the big O notation. So, let us consider some example. Consider a series with nth term as 2 square, which is a number of terms in the numerator and number of terms in the denominator. In the numerator, we have product of 2 square, 4 square up to 2n minus 2 square, and in the denominator we have products of 3 square, 5 square up to 2n minus 1 square. Then it is easy to observe that limit of an plus 1 by an exists and equals 1. Thus, ratio test in this case is inconclusive. However, if we calculate the ratio an divided by an plus 1, we get 1 plus 1 by n plus 1 by 4n square, which can be conveniently expressed as 1 plus 1 by n plus big O of n to the power minus 2. Hence, we can use Gauss's test to check the convergence, and using Gauss's test we find that this series diverges. Next, consider again the P series. It is very natural that the ratio of an and n plus 1 comes out as 1 plus 1 by n whole to the power p, which can be further written as 1 plus p by n plus big O of 1 by n square, and therefore the series converges for p greater than 1 and diverges for p less than equal to 1. In our next topic, we shall discuss sequence of functions. Actually, in many applications, we actually get a sequence or series involving some real variable x. For example, one can consider power series distributions, log series and E series as a function of x. So, whenever we write some series, this type of series in summation, we get two variables, one is n and the second one is x. Thus, in addition to n, there is always an additional variable x. Naturally, convergence concepts are to be reformulated taking into account the presence of x. So, let us formally define this. Let capital A be a non-empty subset of real line. Suppose for each n, for each integer n, fn is a mapping from A to R. That is, fn is a function from A to R. Then fnx is defined as a sequence of functions on A to R. A is defined as a domain of the sequence of functions. For example, we can consider x to the power n, where x belonging to minus 1 to plus 1, e to the power minus nx, x belonging to the whole real line, or sin nx by n, x belonging to the whole real line, as examples of sequence of functions. It is easy to observe that for each fixed x naught belonging to capital A, we get a real sequence fn x naught. That is, if we fix x naught, then the sequence of functions reduces to the ordinary numerical sequence. So, next we shall, after defining some sequence of functions, it is natural to consider the convergence concepts. So, we have already introduced the convergence concepts for a real sequence an, but in this case we have an extra variable x. Thus, it is intuitively clear that we need to develop separate convergence concepts depending on the role of x. For example, consider x to the power n, x belonging to minus 1 to plus 1. For x equal to half, we get the sequence half to the power n, which converges to 0 for large n. However, if we take x as minus 1, the sequence oscillates between minus 1 and plus 1 and hence diverges. Thus, depending on x, the sequence either converges or diverges. So, we have seen how big O and small o notations are useful in defining rates of convergence. We have in particular illustrated use of big O notations in the context of Gauss's test. We have also given some examples, and then we have discussed convergence, pointwise convergence of some sequence of functions, and in our next module we shall discuss some further examples on pointwise convergence and introduce the concept of uniform convergence of sequence of functions and also give some examples.